The last session is going to be about connections, connecting the observations to models, connecting terrestrial models to ocean models, and connecting biogeochemical processes and physical processes, biogeochemical to physical models. So the first speaker is going to be Steve Lohrenz.
Okay, thanks Maria for inviting me to be a part of this panel. And I just want to acknowledge my co-authors and their various institutions. This was definitely a team effort and a lot of different groups involved. And of course also acknowledging our funding. A lot of the work I'll be talking about today has been funded by the NASA Carbon Monitoring System program. So our approach is to, and I guess I'm digressing a little bit from the themes of some of the previous talks. This is a little bit larger scale. Our area of study was the Mississippi River Basin and the northern Gulf of Mexico. And our approach has been to look at a combination of terrestrial biogeochemical models and a coastal ocean biogeochemical model, physical biogeochemical model. The terrestrial model is operated by Han-Chin Tian and his team at Auburn University, and it has various modules: plant physiology, biophysics, soil processes, and then the runoff, the transfer of materials to the watershed and ultimately to streams, rivers, and then the ocean. And that provides input then to the ocean model, which that has been handled by a team at North Carolina State University and also George Zhu, who's now at LSU, as well as Katja Fennell at Dalhousie. And Katja's been responsible for the biogeochemical component of that. The physical portion of that model is based on the HICOM ROMS coastal model system. And so putting that together, then we have this system where we have a terrestrial model that can feed into this ocean model, and it allows us then to start to look at, first of all, what are the different factors that are influencing the transport and the composition of materials coming into the system, and then also the consequences for the coastal margin and biogeochemical processes and carbon dynamics. So just to give you an example, here's some results from the dynamic land ecosystem model. And so what this shows over, first of all, on the right-hand side is the domain. This is total organic carbon leaching for the Mississippi River Basin, and then dissolved inorganic carbon leaching, so you get a spatial representation of those processes. And we're also then able to project into the future using land use scenarios and atmospheric carbon dioxide projections, and also isolate effects of either the climate forcing, which would be precipitation, temperature, relative humidity, etc., as opposed to the atmospheric CO2 effects, as opposed to land use activities, which are derived, those scenarios are derived from the USGS databases. And so what we see then is a projection for increased river discharge over the 21st century, and similarly for DIC, we see an increase in DIC, and these are for, in this case, for a high carbon scenario, the A2 scenario, and for the DIC, similarly, both high and lower, either the A2 or B1 scenarios, and they're sort of captured in that shaded error bar area. So here we have then an example of where we're taking the output from the DLEM model, in this case, dissolved inorganic nitrogen export, and we're comparing early 20th century to early 21st century. And of course, many of you may be aware there's been a large increase in dissolved inorganic nitrogen input in the Mississippi River system as a result of fertilization and agricultural activities. And that's led to an increase in primary production, and that's illustrated here. You can see in this difference map for primary production, much higher productivity in the 21st compared to the 20th century, early 20th century. And analogously then a lower PCO2, so this is having an impact on, obviously on the air sea flux of carbon dioxide in that system. And the model can also generate cross-shelf and along-shelf fluxes, in this case of nitrogen, and that's just shown here for illustration. So to wrap it up then, we have this modeling system, this integrated modeling system that really can serve as a decision support tool. And it allows us to look at these scenarios, which can be used to guide policy development and management, not only for carbon management, but also for potentially eutrophication, hypoxia, and ocean acidification. And an example of that is we've worked with the USDA Environmental Markets Division to help them in trying to incentivize agricultural practices that might, for example, reduce nitrogen export and also manage water quality and that type of thing. So I'll stop there.